Hey y'all, welcome back to my channel. My name is Jeffrey. In this video, I'm going to discuss the autonomic nervous system because I was thinking, if a neurosurgeon can lecture on this topic, then surely I can too, right? So when you think autonomic nervous system, you're going to think automatic. And the reason for that is because this is not within your voluntary control. You and I can voluntarily think, look, I'm going to lift my arm 90 degrees, right? That's very easy for us to think and do, but when a bear starts popping out of nowhere and charging at us, we're not going to be voluntarily thinking, look, I'm going to dilate my pupils so I can see a little bit better. I'm going to take blood away from my gut and give it to my muscles so I can run a little bit faster. No, that's going to automatically happen, right? So for your autonomic nervous system, it's going to be split into three different parts. It's going to be your sympathetic, your parasympathetic, and your enteric nervous systems. Now, I'm not going to touch on enteric too much because the other two are just so much more interesting. And your sympathetic nervous system is going to be in charge of that fight or flight response, like kind of what I was mentioning before with the bear. And your parasympathetic nervous system is going to be in charge of that rest or digest response, which is going to be after a good meal, right? You're going to, your eyes, your pupils are going to constrict because you don't need to use them as much. Your lungs are going to constrict because you're not needing them as much. You don't need a ton of oxygen to um, digest some food. Your heart rate is going to slow down. And for example, your GI tract is going to have a little bit more blood flow. Your urinary bladder, for example, is going to allow you to pass urine more readily. And when you contrast that with the sympathetic nervous system, your eyes are going to dilate, your salivary glands are going to produce more viscous secretions of your saliva. You're going to have airway dilation because you need more oxygen when that bear is charging at you. You're going to increase your heart rate to circulate that oxygen, right? You're going to take blood away from your gut so that you can donate it to your muscles. So the two work in concert, right? The two are in equilibrium with one another. They're going to be very opposite to one another. And but you have to think about it in the sense that they're still dealing with the exact same organs, right? They're still innervating the exact same areas. So now that we have a general understanding of the sympathetic and parasympathetic nervous systems, let's dive right into the different receptors that these systems use, right? When you think about sympathetic, I want you to think adrenergic receptors. And adrenergic receptors always use neuroepinephrine, right, as its neurotransmitter. So when you think adrenergic, always think neuroepinephrine. And when you think sympathetic nervous system, always think adrenergic, okay? And now that we have that out of the way, we have to think about the different subtypes of the adrenergic receptors, right? So it's going to have that alpha and beta adrenergic receptors. You probably have heard of beta adrenergic receptors. They're very common, right? But these two are going to be your two major adrenergic receptors, and these are all split up, right? They're going to be split up into alpha 1, alpha 2, beta 1, beta 2, beta 3. Okay, so it's a lot of different receptors, and what you got to think about right here, and something that's going to be very helpful is going to be this acronym. It's called KISS. And the reason why I say KISS is because um, for your alpha 1 adrenergic receptor, it's going to be a GQ pathway. It's going to be a GQ GPCR pathway. If you don't remember what a GPCR is, it's a G protein coupled receptor, and it's going to induce some effects. Okay, your alpha 2 is going to be your GI pathway, and your beta, all three of your betas are going to be your GS pathway. Okay. So now that we have that out of the way, you can see why the acronym is called KISS, right? So your GQ pathway is going to activate phospholipase C. It's going to cleave, leaving you IP3 and DAG. Your IP3 is going to increase the levels of calcium in the cell. Calcium is going to bind to DAG, allowing for PKC phosphorylation and all those downstream effects. Your GI pathway is going to be inhibitory, and it's going to act directly opposite to your GS pathway, and it's going to block the activation of adenylyl cyclase. So adenylyl cyclase cannot make cyclic AMP. Cyclic AMP therefore cannot, for example, phosphorylate protein kinase A, right? And have all those downstream effects. And then if you look at the GS pathway, it's going to be obviously the exact opposite of your GI pathway. So it's going to activate adenylyl cyclase, it's going to activate cyclic AMP, and it's going to activate PKA and all of its downstream effectors. Okay, so now that we have that out of the way, now that we understand that there's going to be an alpha and a beta adrenergic receptor, and there's going to be different types of those receptors, we have to think about how neuroepinephrine travels from that presynaptic cell to that postsynaptic cell, right? So in the presynaptic nerve, that nerve is actually not going to have inherent tyrosine, okay? And if we think about tyrosine, the reason why that's important is because it's the precursor to your neuroepinephrine, okay? So what is going to happen is that first you're going to shuttle in tyrosine from the cytoplasm, and it's going to be transported into the neuron by something called system L. And that's going to make it go into the neuron, okay? And once it's inside of the neuron, it's going to be turned into a different compound called L-DOPA, right? Which is actually the precursor or an intermediate to your norepinephrine, and it's going to be turned into that by this enzyme called DOPA decarboxylase, okay? Decarboxylase. And once it turns into L-DOPA, what that's going to happen is that this is going to be packaged into some vesicles, okay? So into your synaptic vesicles. Okay, so L-DOPA inside of your synaptic vesicles, and it's going to be packaged there by an enzyme called VMAT, which stands for vesicular monoamine transporter, because your dopamine is actually a monoamine, okay? So once it's transported into these synaptic vesicles, inside of those synaptic vesicles, this L-DOPA is actually going finally to be made into neuroepinephrine, okay? And once it's made into neuroepinephrine, then you can release those synaptic vesicles and have that norepinephrine bind to those different receptors that we were talking about before. And the enzyme that catalyzes this reaction is called dopamine beta hydroxylase. Okay? So now that you understand what happens, so your tyrosine is going to be shuttled into the neuron by your system L, and once inside the neuron, an enzyme called DOPA decarboxylase is going to decarboxylate it, turning it into L-DOPA, which is the biological form that you use in your body. You're going to have your vesicular monoamine transferase transporter transporting that L-DOPA into these vesicles, and inside of those vesicles you're going to have your dopamine beta hydroxylase hydroxylizing it into neuroepinephrine, okay? And then once it's in the synaptic cleft, so once you release this outside of the neuron into these synapses, once it's in the synaptic cleft, it's going to bind to those alpha or beta receptors, right? Alpha beta receptors, and it's going to induce its effect. Remember the KISS acronym. And then after a while, after it's released, that neuroepinephrine is eventually going to bind to the alpha 2 receptors. And remember, this is inhibitory, right? Remember, it's GI of itself, of the presynaptic neuron, okay? And the reason for that is because you don't you obviously don't want this norepinephrine in that synaptic cleft for an indefinite amount of time. You only want it in a very short amount of time, or else you're going to have very devastating results. Because remember, these are GPCRs, right? These have a very magnifying effect. And then, this is going to result in the inhibition of norepinephrine release. Okay, so you're going to stop releasing it because remember, this is a GI pathway. It's going to stop it very, very quickly. And then norepinephrine is going to diffuse back into the presynaptic neuron um, through a channel, right? It's a sodium gated channel, sodium symport diffusion by your NET channel, and that's going to be your NA, your sodium dependent neuroepinephrine transporter. Okay. All right, so that's your sympathetic nervous system. Let's move on to your parasympathetic nervous system. Okay, so parasympathetic, remember, we were talking about before that sympathetic always think adrenergic, right? So what do you always think about when you think parasympathetic? You got to think cholinergic. Okay, when you think cholinergic, the only neurotransmitter that should come to mind is acetylcholine, right? Cholinergic, choline, acetylcholine. So this is always going to act on cholinergic receptors, and your parasympathetic nervous system is always going to be cholinergic. Okay, and your cholinergic system is going to have two different types of receptors, like we said before, but this time it's going to be your muscarinic receptors as well as your nicotinic receptors. Okay, so they're going to be slightly different. They're going to have a very weird name compared to alpha and beta, right? But here we have your muscarinic and your nicotinic. And your muscarinic is actually going to be divided into many different units. Like we said before, remember beta had like 3 different units, right? So muscarinic is going to be M1, M2, M3, M4, and M5. Okay, it's going to have 5 different types of muscarinic receptors. And there's an acronym for this. The acronym is called KICK. And it only applies to those first 3 muscarinic receptors. And you might be thinking, why? Why does it only apply to those first 3? Because we don't actually care about these 2, even though I'll tell you right now that this is going to be your GI pathway and this is going to be your GQ pathway. The fact is that we don't really care about these 2 just because they're not that interesting, to be absolutely honest, okay? And like what we said before, your M1 is going to be your GQ, your M2 is going to be your GI, and your M3 is going to be your GQ once again, as with the acronym, right? So I'm going to talk a little bit about what these 3 receptors do. So your M1, your muscarinic receptor, is actually going to be in charge of your brain and your autonomic ganglia. Okay, your M2 is going to be your presynaptic nerve terminal, as well as your heart, and your M3 is going to be in charge of many different glands as well as your smooth muscle. Okay, so when we think about that, we're going to look at your GQ pathways once again, that PL phospholipase C, and then your GI pathway is going to be your adenylyl cyclase, right? So now that we talked about the different muscarinic receptors, there's also going to be nicotinic receptors. There's going to be 2. There's going to be N1, N2. N2 is also going to be your neuronal, and your N1 is going to be your muscular. Okay, and the reason I say this is because nicotinic is going to be your sodium potassium channels. Okay, your muscarinic is going to be GPCRs. Okay, so your sodium potassium channels, your type 1 is going to be your muscle, and your type 2 is going to be your neuronal. So, for example, in charge of that autonomic ganglia once again, as well as your brain. Okay. Um, so now that we talked about these two, let's talk about once again. Before we were talking about the synthesis of your norepinephrine. Now we have to talk about that synthesis of acetylcholine, right? So for acetylcholine, what happens is first you have your acetyl-CoA from your mitochondria, right? Your acetyl-CoA from your mitochondria, and it's going to be synthesized, and it's going to actually be transported into the neuron because it was from the mitochondria before. It's going to be transported into the neuron by this enzyme, and it's going to be a channel, and it's going to be CHT1, and that's going to be your sodium symport channel, and it's going to be your rate limiting step in this situation because you only have so much acetyl-CoA that your mitochondria can spare and give to your neuron. Okay, so your acetylcholine, um, that's going to be your first step, and then you're going to synthesize your acetylcholine in your neuron by this enzyme. It's going to be called CHAT. It's going to be choline acetyltransferase. So you're going to add an acetyltransferase to the choline, and I totally messed that up. Just like we were talking about before with the sympathetic nervous system and how we synthesized norepinephrine, we have to talk about how we synthesized acetylcholine in your parasympathetic nervous system. Okay, so first we're going to have acetylcholine, acetyl-CoA from your mitochondria. So that's going to come directly from your mitochondria into your neuron, and you're also going to transport in choline. Remember acetylcholine. You're going to transport in choline into your neuron through an enzyme, through a channel. It's called CHT1, and that's going to be a sodium symport. Okay, so it's going to bring in sodium as well as choline, right? And this is going to be a rate limiting step because there's only so much choline outside the cell. And you're going to you're going to take both of these and you're going to synthesize acetylcholine, very simple as compared to before, acetylcholine through this enzyme, and it's called CHAT, okay? It's going to be CHAT, and that's going to be your choline acetyltransferase. So it's going to take an acetyl group from the choline and transfer it onto your acetyl-CoA, okay? And as a result, now you want to package that acetylcholine, right, into vesicles. So you're going to use VACHT. Okay, so it's going to be called your vesicular, right, acetylcholine transporter. So it's going to package that acetylcholine into your vesicles, and your acetylcholine is going to be released in the presence of an action potential and an influx of calcium, right? So when your cell rapidly depolarizes, when there's an action potential, there's going to be voltage gated calcium channels that open, and as calcium rushes into the cell, that actually lets the neuron know that, look, I need to release my vesicles. Okay, and so once the vesicles fuse with the presynaptic terminal, it's going to those neurotransmitters are going to be released into the synaptic cleft. And as they're released into the synaptic cleft, that acetylcholine is going to bind to your cholinergic receptors, right? So acetylcholine binds to your cholinergic receptors, and remember, it's going to be the M1 through M5, right? And as it binds to those receptors, what's going to happen is eventually it's going to bind once again to its the presynaptic cell, and it's going to bind to your M2 or M4 receptors. And the reason why I say that is, remember, M2 and M4 are your GI, your inhibitory pathway. So that's going to eventually, very quickly lead to the inhibition of acetylcholine release. Okay, so that's going to inhibit your acetylcholine release, and eventually you're going to have an enzyme that's called ACHE, acetylcholine esterase, right? That is going to split that acetylcholine into choline and esterase, acetate, sorry, acetate. Okay, and that is going to be the end of that pathway. How long was that, right? One last thing I wanted to talk about was the anatomical structure. So if we look at the spine here, um, at the brainstem and in the sacral region of your spine, that is going to be your parasympathetic nervous system, okay? So your sacral and your parasympathetic is going to be at your brainstem right here. And then the rest of your spine is actually going to be where your autonomic nervous system is, your sympathetic nervous system is going to be held, which is that T1 region to that L3, L4 region, okay? So that's just going to be where anatomically they're located. But once again, remember that these two are in equilibrium so that they innervate different regions, but they're also the same region. So if we're looking at the heart, somewhere here, both your sympathetic and your parasympathetic is going to innervate to your heart. Okay, so I hope that this video has been helpful. It certainly has been very challenging for me to understand conceptually, and I hope that I've been able to verbalize this both through my mouth and through this video visually. So I'm kind of brain dead. So I hope that you had a good time and have a great day.